Hello and welcome to the BigML tutorial series. In this video, we will be discussing logistic regression. We will begin with an introduction in which we will see how to create a logistic regression in the typical BigML workflow using a one-click action. This demonstration will reveal the primary purpose of logistic regression, which is to create models for classification problems. The second thing we will see is that rather than predicting the class with an associated confidence, like a decision tree model, logistic regression predicts the probability of a specific class. In the basic features, we will explore the configuration options available for creating a logistic regression, including how to handle missing values, how to control the stopping criteria with EPS, the impact of something called regularization, and how to control scaling and why this is important. We will also show the coefficients that logistic regression computes, as well as the extended statistics that are available. And finally, in the advanced features, we will explore the field codings and why they are important, how logistic regression compares to models and ensembles, and how to deal with nonlinear relationships between the inputs to the logistic regression and the objective that is being predicted. So what is a logistic regression? The first thing to understand is that logistic regression is a classification model. That is, it builds a model which predicts a categorical value like true, false, yes, no, or perhaps red, green, and blue, or any list of discrete values. If you've completed the tutorial for models, then you may find this confusing. With models, you were introduced to the concept of a regression model, meaning the predicted output is a real number, for example 5 or 2. And for a classification model, the predicted output is a categorical value or a class, like true or false. And so here we have something called a logistic regression, which is for classification. The important thing to keep in mind is that the regression in the name logistic regression refers to how the algorithm works internally and does not refer to the type of model that it creates. So it is important to remember that despite this potentially confusing name, logistic regression is for solving classification problems only. The second thing about logistic regression is that the output is not actually the class value, like true or false, but the probability of a class. For example, 76% probability that churn is true. Of course, we say that the most probable class is the predicted outcome. And finally, the process of creating a logistic regression involves fitting something called a logit function to the data. This is important because it means, as we will see in the advanced section, that it is possible that logistic regression cannot find a good fit for your data without transformation. That is, logistic regression relies on an underlying structure in your data. This differs from decision tree models, which are more flexible in that they discover how to fit your data and do not rely as much on intrinsic structure. So let's take a quick look at creating a logistic regression and explore the visualizations that are provided. For this demonstration, we'll be using the UCI diabetes dataset. As a quick review, this dataset gives us several diagnostic measurements for a group of patients. For example, the number of times they have been pregnant, or their 2-hour plasma glucose level. And then we have a categorical value, which is whether or not each one of the patients does or does not have diabetes. And so we want to use a logistic regression to predict, based on these diagnostic measurements, if a new patient might have diabetes. We will launch a one-click logistic regression, which will use all of the preferred fields to predict the last column of the dataset, which in this case is the diabetes field that we want to predict. Now, because logistic regression outputs a probability, the default visualization for logistic regression is a probability curve. In this case, we have two possible outcomes, true and false, for diabetes, and we can see the complementary probabilities in one dimension. In this case, the 2-hour plasma glucose. As we can see from this prediction window in the upper right, the orange line is showing us the probability that diabetes is true as the plasma glucose increases. whereas the blue line is the probability that diabetes is false. So for a low value of 2-hour plasma glucose, we can see that the probability is that diabetes is false, and at a crossover point of around 150 or so, it becomes more likely that diabetes is true. Now, to draw this graph in one dimension, the other features, like the number of pregnancies or the BMI, are being held constant. We can discover how changing those fixed values impacts the probability curve by adjusting them in the input field selectors here. For example, right now the number of pregnancies is held at 3. We can increase it to, say, 9. And this will show us how the probability curve with respect to the plasma glucose will change in response to this number of pregnancies. In this case, a higher number of pregnancies is shifting the probability of diabetes being true to a lower value of the 2-hour plasma glucose. Similarly, we can try the other fixed variables to discover the impact they may have. Of course, we can also change the variable that is displayed in the one-dimensional graph. For example, we can change the visualization to show us the probability of diabetes with respect to BMI. In this case, we can see that the probability of diabetes being true, that is greater than a 50% probability, occurs around a BMI of about 29. It is also possible to see the decision boundary of the logistic regression in 2 dimensions with the 1D, 2D switch here. This visualization is very similar to the PDP for decision tree models and allows us to select 2 variables. In this case, the plasma glucose is on the x-axis and the BMI is on the y-axis. And in the visualization, we can see the decision boundary between the 2 probable outcomes of diabetes false and diabetes true with respect to these 2 variables. Of course, we can change the variables if we would like to explore the decision boundary with respect to 2 different variables. And once again, we can measure the impact of changing the fixed values on the decision boundary. In this case, we can see a greater probability of diabetes being true for a lower BMI across all ages as the pregnancy increases, and a lower probability across all ages as pregnancies decreases. One thing we did not look at in the introduction to logistic regression is the coefficients that are generated. These are the actual output of the logistic regression process, and they can also be examined in the interface. A few details about these coefficients. A negative coefficient indicates a negative correlation. Similarly, a positive coefficient indicates a positive correlation. Also, a larger coefficient indicates that the specific feature has more relative impact on the outcome, and a smaller coefficient has relatively less impact. This is not strictly the same as feature importance that we see in decision tree models, but does give a quick indication of the relative importance of the features. BigML will also create a coefficient for missing values, if any exist, and the feature to do so is enabled, which we will discuss on the next slide. And finally, for a binary classification, like true-false, the coefficients will always be complementary, since the probabilities must add up to 1. So let's return to that diabetes example and see the coefficients that were computed. So in the main logistic regression visualization, clicking on this button here will take us to the table of coefficients. In this case, we can see something called bias, which we will explain shortly. And we can also see each of the features that are inputs in the training. So for example, we can see the plasma glucose has a coefficient for predicting the outcome of false of minus 1.1. This means that the plasma glucose is negatively correlated with the probability of diabetes being false. And as we can see, minus 1 is quite a bit larger than the other coefficients, giving us the indication that plasma glucose is a dominant feature in predicting the outcome. As mentioned on the previous slide, because this is a binary classification problem with outcomes of true and false, we can see that the coefficients for the outcome of true are just the complement of the coefficients for false. In this case, instead of minus 1.1, it's just 1.1. And now we can see that there is a positive correlation between the plasma glucose and the outcome of diabetes being true, which is what we saw in the graph. As the plasma glucose increased, the probability of diabetes being true also increased. We can also see that there are several coefficients, all with values of 0, that have been automatically added to handle the case that any of these input features had missing values. In this case, none of our input features have missing values, which is what resulted in all these coefficients being determined as 0. Before we show the next example, let's explore the configuration options that are available for logistic regression. The first configuration option controls how logistic regression should handle missing numeric values. There are 3 possible combinations. First, you can enable a default value, which will be substituted for missing numeric values. Second, you can enable the option missing numerics, which will allow the logistic regression to learn from the missing values. For example, if in a loan application the description of why the customer wanted a loan was missing, this could be a signal that the model could learn from, which might indicate that the loan is a high risk. The idea being that if they do not want to tell you why the loan is needed, they may be less trustworthy. This feature is similar to the missing splits feature that is available in the decision tree models. Finally, you can disable both of these options, in which case any rows of data with missing numeric values will simply be ignored during training. If every row has at least one missing numeric value, this will cause the logistic regression to fail since it will have no training data. It is generally better to choose one of the first 2 options for handling missing numerics or to clean them up in the data transformation stage. The next option is the EPS. This controls the stopping criteria. So the process of building a logistic regression is iterative, with each cycle trying to improve the quality of the model. The EPS sets a criteria for how much improvement is required to decide if the modeling process should stop or continue. A higher value of EPS will make the logistic regression complete faster, but the resulting model will generally perform worse than if the EPS was smaller. The Stats button enables extended statistics for the logistic regression coefficients, for example, the p-value. These statistics are important when you need more detailed information about the individual coefficients. It is disabled by default because this information is not always required, and computing it makes the logistic regression run slower. In the advanced configuration options, we have first the weights. These are the standard options for handling unbalanced classes, automatic balancing, or weights per objective class that you've probably seen in the modeling module. In the scaling options, we will see a bias term. If enabled, this allows the logistic regression fit to include an intercept term. This is especially important if your data has a non-zero output when the inputs are all 0. The bias is enabled by default and will generally result in a better model. It is provided as a configuration option for the rare case that disabling it is required and should generally be left enabled. Autoscaling adjusts the numeric values in your dataset so that they have the same scale and will therefore contribute equally to predicting the output. A good example of why this is necessary is to consider modeling housing data. Numeric values that describe homes can have very different scales. For example, the number of bedrooms might typically be a number between, say, 1 and 5, and the square footage could range from a few hundred to perhaps tens of thousands. Because of the way logistic regression works, this difference in scale will impact the weight attributed to each of these variables. In this housing example, the square footage would end up being much more important for predicting the outcome than the number of bedrooms. This is typically not the way numeric values should be treated, and so autoscaling is enabled by default. There may be unusual cases where this behavior of scaled numeric values is desired, in which case this option can be disabled. Finally, there is something called regularization. As we saw in the previous demo, when generating the logistic regression, a set of coefficients for each feature is computed. In order to ensure that the logistic regression is stable, it is better that the coefficients stay relatively small. The regularization affects how the computation restricts the growth of these coefficients. Choosing L1 prefers to keep only individual coefficients small while letting others grow large. L2 tries to keep all of the coefficients small. In the absence of a specific requirement, L2 generally gives a better overall performance and is the default option. One additional thing that we need to mention is how logistic regression handles multiple classes. So in the previous diabetes example, there was only 2 possible classes, true or false, indicating whether or not a patient had diabetes. However, it is not uncommon for a classification problem to involve multiple classes. As a trivial example, we could consider a model which predicts a person's favorite color from among red, green, and blue. We did not have to worry about this situation with decision tree models or ensembles because multiple classes are handled transparently. However, the logistic regression calculation only computes the probability of binary classes. To solve this, the logistic regression algorithm handles multiple classes using a process known as one versus all. For example, we could build a logistic regression for red versus not red, green versus not green, and blue versus not blue. And then to compute the final result, these separate logistic regression computations are combined into a single probability for each class. This sounds difficult, but fortunately it is handled transparently by BigML. So let's return to the UI and see an example of these configuration options as well as the handling of multiple classes. So for this demonstration, we'll use the user profiles dataset, which contains user preference information for things like how the individual prefers to dress, whether that be elegant, formal, informal, or they have no preference, or perhaps the situations where they enjoy drinking, whether they prefer to abstain, whether they're casual or social drinkers. We also have features like whether or not they are smokers, and the latitude and longitude of where they live. We will use this dataset to try to predict the drink level based on these preferences. So instead of a binary class, we will now have 3 possible outcomes: abstaining, being a casual drinker, or being a social drinker. So this time, rather than do a one-click logistic regression, let's go into the gears icon and configure the logistic regression. Similar to the model configuration, we can choose the objective field. In this case, we want to predict the drink level. Here we can see the default numeric value that we were describing before. So for any of the numeric values that might be missing, we can set a default. For example, the maximum, the mean, the median, the minimum, or a 0 value. Or if we like, we can let logistic regression handle missing numerics as a potential signal. By unsetting this option, it will just ignore missing values, but by setting this option, it will create a coefficient specific to missing numeric values. Here we see the selector for choosing the EPS value. Again, setting the EPS higher will allow logistic regression to complete faster, but will tend to give us worse performance. Here we see the button that enables the extended statistics. Again, enabling this will slow down logistic regression, but will give us much more detailed information about each of the coefficients that is computed. In the advanced configuration panel, the first option available is the weights, similar to the decision tree models. We can choose from balance objective or objective weights. In this case, let's go ahead and balance the objective. In the scales panel, we can see the option to enable or disable the availability of the bias term, as well as whether or not the fields will auto-scale. By default, the bias term is enabled, and auto-scaling is also enabled, as we can see in the information shown here. One block down, we have the regularization settings, where L2 is chosen by default. We didn't mention before, but there's a strength parameter, which basically controls how strongly this regularization is applied. A higher value reduces the effect of regularization. In the panels below this, we can see that there are also options for configuring the sampling, much like the decision tree models. These are applicable if you wish to build your logistic regression with just a sample of your dataset instead of using the entire dataset. And you can control things like if the sample will be deterministic, if it will use replacement, etc. Let's go ahead and build this logistic regression and see the output. The first thing we'll notice that is different from the diabetes example we did before is that there are now 3 graphs. And this is because this classification problem has 3 possible classes. As we can see in the prediction window, the blue line is the probability that this individual abstains from drinking, whereas the orange line is the probability that they're a casual drinker, and the green line is the probability that they're a social drinker. In this visualization, we're currently seeing the probability of each of these possible drink levels with respect to the user's longitude. We could change this to latitude, where we can now see that as we move further north, it becomes more likely that the individual abstains from drinking than they are a casual drinker or that they are a social drinker. Now remember, this is only in one dimension, and the other variables are being held constant. So let's see what the impact is across latitudes if we change whether or not this person is a smoker from false to true. Now you'll notice that the orange line barely moved. This is the probability that they are a casual drinker. And so this probability isn't changing very much with respect to whether or not they are a smoker across latitudes. However, the green line, which shows that the probability that they are a social drinker, has increased dramatically across all latitudes by changing smoker from false to true, and also the probability that they abstain has become much lower. And so we can see that there appears to be quite a correlation between smoking and drinking in this case. Of course, we can also see what the decision boundary in 2 dimensions would look like. For example, on the y-coordinate, we could put perhaps the activity that the person likes to engage in, and on the x-coordinate, we could put the ambiance that they prefer. And so now we can see a pattern where if you're unemployed, there's a high probability of abstaining, and especially also if you're unemployed and prefer a solitary ambiance, you have a very high probability of abstaining. Let's switch over to the coefficient view and see how that looks for 3 classes. So now we have the 3 possible outcomes: abstaining, being a casual drinker, or a social drinker, and we can see the respective coefficients for each variable. So here for the latitude, we have the coefficient for abstaining, the coefficient for being a casual drinker, and the coefficient for being a social drinker. And because we've enabled statistics on this, we can actually look at each one of these variables and see whether or not it's a significant coefficient, and in addition, the p-value, the z-score, the confidence interval, and the standard error. We can also see that something interesting has happened for the categorical inputs. For example, the variable smoker has 2 possible inputs, true and false. And you can see that we've generated 2 separate coefficients, one for when smoker is false and one for when smoker is true. And so this is showing us a little bit of an insight into how categorical inputs are handled. As we saw before, further down, we'll discover that there are coefficients for the possibility that each one of these features has missing values. So in fact, actually we had several missing values for the smoker feature. And so we end up with a coefficient being generated for the case where this feature has a missing value. So now let's explore the advanced features of logistic regression. The first is something called field codings. The idea here is that logistic regression is expecting numeric values in order to compute the coefficients. So how are things like categorical values in the input features handled? The default technique, which happens transparently, is called one-hot encoding. Basically, the possible classes are converted into a vector to indicate which class is selected. For example, if the original feature is a categorical field with values like red, green, or blue, or possibly missing, then we replace this with 4 new features. The first is a feature which indicates that the color is red and is therefore a 1 if and only if the color was red, and 0 otherwise. Similarly for the other possible classes of the original color field. This is called one-hot encoding because only one of the new features is hot, that is, a value of 1 for each possible class. In some special circumstances, changing the way this coding is performed may be required, and so there are a few other options. The first option is something called dummy encoding. This is basically the same as one-hot encoding in that the classes are converted to a vector of 0s and 1s, but the difference here is that one of the classes is designated as the reference class and is indicated by all the transformed values being 0. The remaining classes are then encoded the same as one-hot. As you can see, this requires adding 1 less new feature. Before we had 4, and now there are only 3 fields. The selection of the reference class is typically the most common class in an unbalanced situation, or is chosen because of a specific desire to essentially have logistic regression treat that class as the default and the other values as being different from that reference class. Now, a third possibility is something called contrast encoding. The idea here is to replace the categorical value with a single numeric value that takes real valued numbers that indicate the relative importance of each class. For example, we could assign the value of 0.5 to red and minus 0.25 to both blue and green, and 0 to missing values. So one way to think about this encoding is that it impacts the logistic regression computation by giving the red class a positive influence on the outcome that is twice as important as the blue and green classes, which additionally have a negative influence. Now, when assigning values, keep in mind that the assignments must sum up to 0, as they do in this example. Now, one question you may have is, which field encoding should I use? And the answer is, it depends. The selection of a different field coding generally indicates that you have a specific requirement for how logistic regression should handle the possible values of a categorical field. If you do not have a specific requirement, then the default one-hot coding is probably the best option. So let's return to the UI for a moment and see where the field codings are configured. So if we return to the data set that we use to compute this logistic regression, we'll be able to see the configuration option for the field codings. Basically, when you're configuring a logistic regression, if you scroll down to the individual features, you'll notice that for each input feature that is a categorical value, there's a little set of gear icons. If you click on this gear icon, it'll bring up the window that allows you to select a different field encoding from the one-hot. In this case, this would be a dummy encoding, and the reference class is selected with this radio button. The next selector enables contrast encoding, where we can specify the relative weights as mentioned previously. The next option for field codings, called Other, I actually didn't mention in the slides, but this is essentially the same as contrast encoding, where you can specify relative weights, but in this case they don't have to sum up to 0. Now we need to discuss the concept of curvilinear logistic regression. The issue here is that logistic regression expects a linear relationship between the features and the objective that you're trying to predict. Now, this is actually pretty common. It means that logistic regression generally works well. However, if your data has a nonlinear relationship, this can greatly impact the quality of the logistic regression model. Fortunately, this problem can be addressed by adding nonlinearity to the features before modeling. For example, if you have a quadratic response in your data, you could square the corresponding feature. Unfortunately, knowing which transformation to try requires either enough domain knowledge to know what might work, or experimentation, or both. So let's see an example of a quadratic relationship and how we can address it when using logistic regression. So for this example, we'll be using the quadratic demo source. And in this case, there are only two features. One is the age. We can imagine this is the age of a patient. And the other is a categorical value called severe case that has possible values of true and false. And the idea is that this data set represents patients that had the flu, for example. And based on their age, we have the knowledge of whether or not each one of these patients had a severe case of the flu or not. So let's use this source and create a data set, and we'll plot it in the dynamic scatter plot so that we can see what the response of the severe case is with respect to the age. So we have the age along the x-coordinate here, and we have the incidences of severe cases of the flu on the y-coordinate. And we can see that there's a pretty strong quadratic response here, in that there's a lot of severe cases for young patients, and a lot of severe cases for old patients, and very few severe cases for people between the ages of roughly 13 and say 65 or so. And so the shape of this data is essentially quadratic. We can see there's a positive response for low values, a low response for medium values, and again a positive response for high values. And so if we try to fit a logistic regression to this data as is, this group of patients will not be modeled very well. And we can actually see that behavior by doing a training and test split and evaluating logistic regression. So let's return to the data set and decide how we're going to handle this quadratic behavior. Now we'd like to try building a logistic regression to predict the severe case with respect to the age. But we'd also like to try handling this quadratic behavior by taking the square of the age. So before we do our training and test split so that we can evaluate logistic regression, let's go ahead and transform this data set so that it has the square of the age property in it. So we can do that by using the Add Fields to Dataset option. And we'll call this new field the age squared. And we'll choose to use a Lisp S expression. And in this case, all we need to do is take the square of the field age. Once we create the dataset, we'll have the new feature that we desired, which is the square of the age. Now let's perform a training and test split. Now that we have the training set, let's first create a logistic regression using only the age. So for this, we'll configure the logistic regression. We'll predict the outcome of a severe case, and we will leave out the square of the age. Let's go ahead and let that logistic regression run. And once it's complete, let's go ahead and do an evaluation. Because we did a training test split, it automatically chose the 20%. So let's go ahead and let that run. And now we can see there's quite a bit of orange here, and we get some warning that this logistic regression model may be giving us poor performance. And in fact, if we open the mode-based comparison, we can see that it's really doing no better than just choosing the most common class. So let's return to the training set and try a logistic regression, including that quadratic term. So this time we'll configure the logistic regression, we'll predict the severe case, but we'll let the model use both the age and the square of the age. Now, once again, we'll perform the evaluation. Again, on the 20% test set. And we can see that the orange warnings are gone and that the F measure is actually quite a bit higher than it was before, and that this model is now performing much better. So now that we have a pretty good understanding of what logistic regression is and how to configure it, let's take a moment to discuss how logistic regression compares to decision tree models and attempt to understand why we might choose one over the other. So the first thing that we have seen is that logistic regression expects a smooth linear relationship with the predictors. And in fact, this is important enough that when we have a nonlinear relationship, we can improve the logistic regression results by transforming the data. This is essentially a non-issue with decision tree models, since they adapt very well to these ragged nonlinear relationships. This means that decision tree models work well with nonlinear data without any special considerations. We also saw that logistic regression gives us the probability of a discrete outcome, that is, a particular class for the categorical objective. Decision tree models, on the other hand, really have no concern. They work with classification, regression, multi-class, it doesn't matter. They all work equally well. With logistic regression, we have lots more parameters that we can get wrong, right? We have regularization, we have the scaling, we have the field codings. And what we see with decision tree models is that they are essentially parameter free. Although it is true that with ensemble techniques, we start having more parameters, such as the number of trees or the random candidates. It is true that with logistic regression, there are quite a few more things to configure. So when to use logistic regression? Well, overall, logistic regression is slightly less prone to overfitting. And decision tree models are slightly more prone to overfitting, although again, this is something that can be addressed by using an ensemble technique. And finally, because logistic regression is fitting a function to the shape of the data, it's essentially making an assumption of the underlying structure. Now, while this can be considered a negative, the truth is that if the structure does exist in your data, then logistic regression may work better when there is only a small amount of training data available. Decision tree models, on the other hand, will not. Instead, you need to have enough training data that the model can discover this structure. So to make this concept of underlying structure a little more clear, let's see an example of modeling a very small data set that has a diagonal structure where the decision tree doesn't have enough information to discover the shape as well as logistic regression does. So for this demo, we'll be using this diagonal edge data set, which just has 3 variables, x, y, and z. And if we throw this in the scatter plot, we can see what the decision boundary looks like. And so we have this very clear decision boundary between the orange class and the blue class, that is z values of 1 and 0, along this diagonal line. Now there's quite a few data points in here, so the decision tree probably won't have too much trouble modeling this diagonal line. So we're going to make it a little bit more difficult by taking a very small sample. So we'll return to the dashboard. And the first thing we'll do, since we want to be able to evaluate these models, is we'll go ahead and do a training and test split. And now that we've split the data, we're going to take our training set that has 800 data points in it right now, and we're going to sample it down and make it incredibly small. So we'll go ahead and sample this data set at a rate of 1%. So now our training data set only has 7 data points to learn from. So let's see how logistic regression compares to a decision tree model when it only has these 7 data points to use. So we'll start by doing just a one-click model. And you can see we end up getting a very simple tree. So let's evaluate this model and see what its performance is over our test set. So we'll take the same diagonal edge, but the test set, and we'll see how the model does. Now it looks like it actually isn't doing that bad, but let's compare it to the logistic regression. So returning to our training set that only has the 7 training instances in it, let's go ahead and do a one-click logistic regression. And let's go ahead and evaluate this logistic regression using the same test set. And so here we have the evaluation of the logistic regression. So let's compare this side by side with the decision tree. And now we can see more clearly that the logistic regression is doing a little bit better on this training set than the decision tree is. Now, if we repeat this and allow more training examples in the training set, the decision tree will eventually do easily as well as the logistic regression. So remember, the idea here is that if your data has an underlying structure, logistic regression may still be able to discover it even with a small training set, whereas the decision tree really benefits by having a large enough training set that it can discover the structure that exists in your data. In summary, in this tutorial we have seen that logistic regression is a classification model which outputs the probability of a class. In the configuration, we discussed how to work with missing values and the meaning of the EPS, regularization, and scaling, and how they impact the quality of a logistic regression model. We also saw how to interpret the coefficients that the logistic regression outputs, as well as how to enable the extended statistics. And then finally, we explored several caveats of using logistic regression, including the fact that it expects this linear relationship, but that we can fix it, and that there are a lot of configuration options, which is good if you must use logistic regression, but otherwise can make a lot of mistakes possible. And finally, we explored the considerations to be made when deciding between logistic regression and decision tree models.